the government has set these quite tough targets of actually being sort of net zero by 2050. And heat represents 50% of all the energy consumption in the UK. That's including commercial as well as domestic. And new existing homes account for 20% of actually carbon emissions. So we have a big factor to play. Very quickly, this is a roadmap of what's going on, what the government set out. So we've got started off with the future home standards. Recently, there's been updates to Part L. You probably heard about the sort of when you're updating a system or putting a new system in, it has to be for sort of low temperature systems. Then we've got the future home standard coming out in sort of 2025. And then we've got something called the Green Growth Challenge 2030, leading up to 2050. This is a slide from Beamer, and you can see here on your left-hand side the different technologies, and you can see predominantly, and then you go see there's some on heat pumps, oil, electric heating, and the general sort of view is that come sort of 2050, it'll be predominantly heat pumps, hydrogen, and other technologies, and also heat networks. So quite a shift. The government's brought out all sorts of papers to actually sort of give the country guidance. This is their 10-point plan, which came out in November 2020. The key one here for us, point 2, which is hydrogen. So the government's backing this at the moment, but they're still waiting for all the technology and infrastructure to be proven. And also they brought out the hydrogen strategy. And you can see that's a statement from Kwasi Kwarteng, where he's actually stated that sort of hydrogen is one of a handful. Also, a big thing that's in discussion at the moment is about a market mechanism where you'll have a quota, a bit like carbon credits, you'll have a quota for producing a certain percentage of actual sort of heat pumps per year. And if you don't produce that percentage, potentially manufacturers will get fined for that. So that's a really big thing for us to sort of try and sort of tackle. Not saying we're particularly happy about it, and there's lots of discussions going on at sort of government level on that. Then 2026, the phase out of fossil fuels for off-gas grids, so like for commercial and domestic oil. And then heat pump cost, same as the target is they're going to try and get a heat pump the same cost as a boiler by 2030. So you can see some massive challenges that they set out. So this really gives you a picture of where we are. So currently here, you can see predominantly the natural gas condensing, and you can see over time how that changes. So if you go to the other side, you can see sort of the proportion of hydrogen, hybrids, air-to-water heat pumps, a little bit of ground source heat pumps, and also heat networks. You know, we've been like this, haven't we, for the last 30, 40 years. So it's a massive sort of upskill for us all as an industry. So the technologies that we have, we've got heat pumps, which is what the government's pushing really hard on. And again, sort of that target to increase the number that we have installed in our properties by 2028, not just on new build. I mean, new build, you can understand why you put a heat pump in, because you can design the property in the right way, with all the insulation, with all the actual sort of modern efficiency methods. Retrofit, but also the government's also is a push for retrofit as well, and also not managed gas. And that's a bit more challenging. Potentially you need to make a lot more sort of changes to your property. For example, my house, it would be impossible to, well, unless I spent about £25,000, it would be impossible for me to actually carry out your combination boiler. There's quite a extra bit of space that's needed. Then we have hybrids. So a hybrid is a combination of a heat pump with a gas boiler. The heat pump is the primary source of heat, and then the actual sort of the boiler then backs it up in those extreme conditions. And also potentially, if you use a combi boiler, you can use that for hot water as well. And a hybrid isn't really just a bi-variant system, it's actually an intelligent system. So you have a series of algorithms within the actual control unit. We've got one just here. And it will calculate based on the outside air temperature and the actual flow temperature which heat source to use. So the way that the consumer deciding on whether to run the boiler or heat pump is taken away from them because it's all done as a package. You can see over here just how the sort of changes. So minus 15, then when you move, as it gets warmer and warmer, the heat pump takes more of the more proportion of the actual sort of the heat output. And then you have electric. I'm not convinced about electric really because in principle they're very cheap, but there's also sorts of sort of social or economic issues with it, especially with sort of like things like fuel poverty. As we know, sort of if you run on electric, you basically sort of at the mercy of the actual sort of utility. And also we have heat networks. So even a heat network is really you have a central heat source which is here, and it supplies hot water for the district heating for the heat network for the district heating system. All the flats and all the houses and all the commercial buildings. I mean, within every property you have something called a heat interface unit, which is a bit like a sort of it's a bit like sort of a
glorified sort of high-performance radiator with a control system and also all sorts of valves inside it. The beauty of that is you can actually just change your sort of what fuel you're using, your heat source, rather than having to actually to change it in all the properties at the same time as well. And then we have the good old condensing boiler that we've been reliant over the last sort of decades. The big thing here is that today we've got over 23 million homes with gas central heating. So that's a massive challenge that the industry's got to sort of overcome. You know, we just can't take all those out, can we? You know, and then we've got 1.5 million boilers that are fired on oil central heating. So those are really the technologies. So now I was going to talk a little bit about hydrogen, because hydrogen, we think, has a crucial part to play. So this is just a sort of a comparison that if you're going to, what you would have to do if you had today, if you had a sort of a combi boiler and you wanted to change it for a heat pump. So the first thing is, sorry, I'll go back again. Take your boiler out, and you're going to have to put in an indoor unit and also an outdoor unit. There's also the option potentially that you could actually have the indoor unit as part of the outdoor unit as well, so there's lots of combinations. Then, because with a heat pump, you can't really sort of use it as in a way that you can with a combination boiler and hot water. You're going to need a hot water cylinder. Heat pumps run on low flow temperatures, 45 to 55 degrees. You know, a lot of our properties at the moment are running on slightly higher temperatures, so we're going to have to potentially, in a lot of cases, change the radiators, potentially the pipework as well. So there's quite a lot of disruption to the consumer for that. And also we've got to change the control system. So we're probably talking sort of weather compensation controls, a bit more sophisticated, so we can actually see the sort of outside air temperature and the flow temperature, and then actually and then sort of feed that back to the actual control unit for the heat pump in the property. Or we could just switch it to a hydrogen boiler. How easy is that? Advantage of hydrogen: no carbon dioxide, because there's no carbon in your fuel. So there's a good, you know, it's a nice little safety case there. Through the testing that we've done at Worcester, we've actually sort of the NOx levels are actually lower, which initially was quite surprising, but it's been proven for all the testing we've done that the actual NOx levels are a lot lower, which means this issue sometimes you get in built-up areas of having all these flues coming out and emitting NOx emissions. That is reduced. It's not eradicated, but it's reduced. So now I'm going to talk a little bit about some of the trials that are going on throughout the country. There's an awful lot going on. It's just not us as a boiler manufacturer, it's the utilities, it's all the sort of people that manufacture sort of gas meters, the valves, producing the hydrogen as well. So currently the gas distribution network is being changed. You probably over the years noticed all the roads being dug up and all the yellow pipework being put underneath. Just by coincidence, that's perfect for hydrogen. You couldn't run a hydrogen supply on the old, iron sort of steel sort of pipework because it would seep through. But for polyethylene, it's the ideal material. And the UK has probably got the biggest gas network in Europe, if not the world, because we've been so reliant on the sort of North Sea gas. So why do we want to waste all that sort of infrastructure? So we have to produce the hydrogen. The ideal way is actually to produce it through electrolysis. So it's created from a renewable sort of source like wind, solar, tidal. It's also least harmful to the environment. We've been told there's a, wind farms are going up, aren't they? You see all these projects off the east coast and all that sort of thing. But also initially, we're also going to have something called blue hydrogen. Blue hydrogen is produced from methane through a process called steam reformation, which is heated at very high temperatures. And a byproduct of that is carbon. So we'll have to store that carbon. And there's a fair few sort of projects, and there's government grants actually for companies that are actually sort of investing in that technology as well. So it's a combination. It's not ideal, but it's a good bridging between us getting to green hydrogen in the future. And the beauty of hydrogen, you can store it, where at the moment you can't really store electricity in the same way, can you? So you can actually store it for a rainy day and use it when it's actually really cold. So hydrogen projects. So this is all the drivers for this is all those government sort of initiatives and policies that's pushing all this. So we've had the H21 project. So that's and then we've had something called High Deploy, which has been looking at sort of 20% hydrogen. There was a trial at Keele University a few years ago where they actually had a sort of load of properties just running on 20% hydrogen. And in principle, you can run a boiler on 20% hydrogen today. You don't need to change any of the components or any of the actual sort of infrastructure for it either. And there's a trial that's going to be happening near Gateshead, 668 homes. We'll be actually receiving blended hydrogen on the grid very shortly. Then High for Heat was a big sort of project initiated by BEIS and the utilities, looking at all the sort of safety cases for hydrogen, all the things you had to consider from production of hydrogen all the way through to the house, like gas meters, gas pipe work, distribution, sort of the pressure within the system that you're in as well. And then there's another project in the northwest that's looking at more for the infrastructure for hydrogen, all the sort of before it gets into your property. So the one coming up shortly is what's called the neighbourhood trial, which is planned for next year. So that's it. That's up at Levermouth in Scotland. And there's going to be a total of 300 homes that are going to be connected to a hydrogen grid. And that includes cookers, gas fires, hobs, etc. They're currently recruiting sort of people to actually sort of live in those properties. They'll be running on hydrogen, so they're new properties. And also what we're also looking at is also how we're going to train the engineers that are going to be working on these appliances. Currently, there's no qualification for hydrogen like there is for sort of a natural gas, like your OCS sort of a ticket. So all the engineers that install those appliances will be actually deemed to be competent on hydrogen. So the installations are going to start hopefully Q3 next year. And the project runs until 2027, which is just after the government decision on hydrogen. And as you can see there, they're looking at using electrolysis wind farms to produce the hydrogen. Goes through the gas storage device, goes into like a large tank where they actually then regulate the pressure to all the properties. Okay, so leading on from, and also these are a couple of projects that are currently sort of being looked at. One in Redcar on the northeast with Northern Gas Networks, and one in Whitby with Cadent Heat, and you can see the big names there. So there's awful lot of actually investment and time going into this. So the hydrogen timeline is that, so we've got single demonstrations going on at the moment. 2023 we've got the neighbourhood trial starting. And also they're doing a study for the actual village trial, which will be sort of up to 2,000 properties on hydrogen. And then 2026 is the big date when the government will take a decision, yes or no. Do we press the green light to actually do it on the large scale to hit our zero carbon targets? And then by 2030, the plan is, all being well, we'll have a whole town fired on hydrogen. But the government's taken a step-by-step approach. We've got to prove the safety case and the performance at each stage before we move on to the next stage. So we've got some product demonstrations at the moment. So we've got one in Spade Adam in Northumberland that's been in for, I think it was sort of end of 2019, beginning of 2020. And we were the first person to actually run a boiler in someone's house on hydrogen. Spade Adam is like an MOD facility, so they were doing lots of tests on the sort of the network as well. There's a showroom over in Gateshead that you can actually go and see a property running on hydrogen. There's nobody living in it, but you can see the boiler running, you can see the cookers and the gas fires running. So the technology is there, it is reality. The key thing about hydrogen is actually how do we upscale it on the large scale. The technology's been there for years and years and years. It's nothing new. And then we have Milford Haven. There was a hybrid demo, so that was actually run as well. So talk a little bit about the hydrogen boiler. So this is a comparison of hydrogen to methane. So that the flame speed for hydrogen is 8 times faster. So we've got to redesign some of the components inside the boiler. And you can see that the actual calorific value and the density is lower. And then therefore that gives and the Robbie index is roughly the same. So basically the hydrogen gas is the same chemical principle as natural gas. But also you can see the ignition energy is also a lot lower as well. So from a sort of a boiler manufacturer's point of view, we're looking, we've been sort of working on this project now for like a couple of years, and there's various sort of technology sort of challenges that we've actually overcome. So, because the flame speed is faster, there's potential for more flashback, so you have to redesign the way the actual sort of the burner operates. The key one there is condensate. Hydrogen produces a lot more condensate than natural gas. Not necessarily a bad thing, because it might actually reduce the potential freezing as you've got more condensate going down the pipework. Materials compatibility. We found most of the materials that we currently use are compatible with hydrogen, like the plastics and all the sort of the pressings and things like that. I mean, the big one is ignition, because there's no carbon in the fuel, so we have to look for different methods of actually sort of measuring the flame. So flame detection, we currently use sort of flame ionisation, because it senses the carbon molecules inside the actual sort of flame. But you can't do that with hydrogen, so we're looking at an optical sensor method. And so that's a hydrogen flame, and that's a methane flame. You can see there's more. It doesn't look that much difference, really, does it? It's the same colour, but there's definitely a difference. And from a sort of a design point of view, you've got to sort of find a way of actually sort of detecting that flame. So how are we going to convert? Do we just change the boiler? Can you imagine if you're going to convert a whole street, and or a whole town, you've got to potentially change 10,000, 20,000 boilers all at once. It's not really practical. The method that's been sort of accepted by the government and the industry is having a hydrogen-ready boiler. So we design a hydrogen boiler that can also run on natural gas. So a typical conversion kit, we think, based on all the research done so far, will be a burner, a gas valve, and a code plug. In a way, that's similar to, years and years ago when we went from town gas to natural gas. That was almost like a similar scenario, wasn't it, really? The difference now is there's a lot more appliances out there that we've got to convert. So in principle, that is reasonably low cost. The big thing is about skills, isn't it, and competency, and how we actually get the actual, us all up there be able to sort of be competent actually sort of working with hydrogen and installing it. So the key thing is that with the initially on the trials, just a few people will be trained to actually do those conversions. But as it becomes more mainstream, we'll see it as a bit like an LPG changeover. And then as hydrogen becomes the predominant fuel, then it becomes the full ACS like you do today. What we can't afford to do is actually, if someone has a hydrogen-ready boiler that's converted, you've got to keep the cost down. So there's a target to keep the conversion kit below £100 of all the component parts, and also the conversion's got to take less than an hour to make it nice and simple and easy. The key thing is that the whole industry is taking out all the risk. In a way, the engineer will just do what they do now with some slight variations. For example, on sort of fuel analysis and maybe testing and purging. So really, when it's an industry, if we're going to hit this sort of net zero home heating target by 2050, it's a diversification of technologies. So it's not one size fits all, which maybe has been a little bit up to date. So heat pumps, sort of semi-commercial heat networks, sort of air to water heat pumps, and also potentially hydrogen as well. Okay, so that's the end of the presentation. Do you have any questions? Sorry? Yeah. Yeah, in principle, if the hydrogen goes that way, it's going to make it a lot cheaper and a lot easier for people just to sort of convert to hydrogen. Because heat pumps are, if the property's designed right, heat pumps are perfect. For a new build property, you can't really argue with that, can you? Because the property's been designed to be extremely high efficient. It's got the U values, it's got the insulation, it's got the triple glazing, all that sort of thing. Yeah. Sorry?
What happens with the rest of it? Because if it's working,
Yeah.
it's working anyway.
Yes.
But if it's not,
Well, there's going to be when we get the green light for hydrogen from the government, all boilers that will be sold will be hydrogen-ready boilers. From a certain date, so by 2050, that 15-year life of a boiler, when you come to replace it, because it's been replaced in the last 15 or 20 years, that basically majority of boilers will be able to be converted. Not 100% hydrogen, no. In principle, you could run them on 20% hydrogen. In principle, yeah. Yes, without changing any components. Sorry? We've only literally agreed to it over the last sort of
Martin can
12
stand by
months.
the heat pump with the grinding in the background. Just see what you think. I'll move that.
have a BUS account and you can offer the grant funding. But obviously it's heat pumps, renewables, you need to have your MCS. Anybody in the group today got their MCS accreditation? No? Okay, so the microgeneration certification scheme is a way of proving that the system has been sized correctly, specified correctly, installed correctly, and it's going to run efficiently and be good for the customer. So to get your MCS, I don't want to put anybody off it, it's something that we have to sort of do, but it is a big thing. It's a big decision for most businesses. It's not easy, obviously there's fees involved as well, but you have to be on the MCS and fit an MCS certified product to actually get the funding. Okay, so obviously our products are MCS, so that's that tick done, but you as an installer have to be part of an MCS scheme in order to get access to the grant funding. And for most installers that I meet, I'm a full-time trainer back at the Worcester and at Banks Mobile, is well, if I'm only going to fit one to see how it goes, that's a big investment to go forward. Or I only have been asked about two of them, so I can't answer that really. It's your decision. Do you want to go down the MCS route and go down that way? That was completely up to you. But we do have a helping hand, and that is there's a company called Alto Energy, and if you were to give them the designs of the new build or the heat loss calculations of a barn conversion you've recently been to, they will then actually size the heat pump, they'll spec the heat pump, give you diagrams to follow, size the radiators, help you with underfloor sizes. They will then commission the unit for you, and you can use their MCS umbrella scheme. Okay, so if you've only got one or two or three, you think, is this for me? Do I want to invest in the MCS? This could be the answer for you, and it's proved very popular. It is by far the easiest way to go, particularly for your first one. So if you have a customer that's serious about having a heat pump, speak to your Worcester local representative. He will then get in touch with them, and then we'll go forward and we'll push it towards Alto Energy to help you out. Okay, so let's move on to the actual heat pump itself. So we have one right there, but that's what it looks like again in real life. One thing that we sort of quite promote, and we think these are pretty generous in the industry, is the guarantee. So obviously we don't offer a warranty at Worcester, we offer a full-on guarantee. And I do apologise for the green on green, but you can offer 7 years on the unit itself, 3 years on the unit itself, and 10 years on the compressor. The actual engine of the unit, the bit that you don't want to go wrong, you do get 10 years. But then anybody who's a Worcester accredited installer can then get 5, 7 on the unit, which is pretty good. Right up there, and also we do cylinders for the heat pumps as well. So we've got a good package with the guarantee for our unit. Okay, so we do two different ones, and it can be a bit confusing from the outside looking in. So the 7001 is the sort of the main seller really. We do that in a 5, a 7, a 9, a 13, and a 17 kilowatt output. The 17 kilowatt will be 3-phase. Okay, because obviously that's a big heat pump. And then if the customer says, well, I want the best absolute efficiency I can get, and I also want the quietest heat pump available, then we do a unit called the 7400, which is the one that's just over there. Okay, so that unit, it's actually if you bought a 5 in that, it's actually the 7, but it's been down, ran at a smaller output to be optimised for efficiency and for noise. And it is a very, very, very quiet and efficient unit. So if that's what the customer wants, we do have a higher end unit. But the sort of the main normal heat pump is the 7001. Okay, so some of the installer benefits that this unit has. It is an inverter-driven compressor. It's also what we refer to as monoblock. So within heat pumps, you'll hear this phrase quite a lot, monoblock or split. So split means that you're dealing with the refrigeration pipes, which means you need to have your F-gas. Yeah, you need to be an aircon engineer to be able to touch those pipes and gas the unit up. But if it's a monoblock, the unit is pre-sealed, has a refrigerant in it, shouldn't have to be messed with for the whole of its life, and you don't need to be F-gas to install one. It's like installing a fridge freezer in the kitchen. So our unit is a monoblock. It has a drip tray involved, so with this type of technology, the unit will remove moisture from the air, which means it will drip moisture into a drain. And there are some units that will just drip all over the floor. Our unit has a drip tray built into it, so you can then plumb straight off the back and put it into a drain or a soakaway. We do call it condensed, but it's not acidic. It hasn't come from flue gases. It is just moisture from the air, so it can go into like a chickpea gravel soakaway. The unit also comes with coastal protection, so the actual back of the unit, the heat exchanger, is aluminium for thermal transfer, and obviously aluminium can be affected by salt if you live near the seaside, and you normally would specify that and pay a premium for that, but our unit has that built in as standard, so it has coastal protection on the heat exchanger. We have a backup immersion heater in our unit, and some people are like, oh, I'm not sure about that, I don't want to use that much electric. If I was to sell you a heat pump that would do everything that the whole year could throw at it, the heat pump would be pretty big, and also you've got to drive that big compressor. So we would size the unit to 99.6% of the time, and on that one night in the whole year where it goes to -10, and the heat pump needs a bit of a helping hand, there's an immersion heater in the unit to give it help it out. Which is much better than having a huge heat pump for the other 354 days of the year. So so it has that built into it already. The unit obviously is monoblock, so we're going to go from the indoor unit, which is this box here. Okay, so you'd have that in the middle in the house, and that'll have a flow and return going into the outdoor unit. And there's no refrigeration, as I mentioned, and we even don't ask you to fit glycol, use glycol in the water, just straight up inhibitor. Obviously the pipes must be heavily insulated. You want to keep them to a minimum, that's just efficiency for you. But we actually say that the unit doesn't need any glycol in it, which is good because the glycol does take some efficiency away. Service friendly, so the whole thing comes apart with only 8 screws, and then inside there is the insulation. It has big straps around it, believe it or not. You undo these straps and the whole thing comes apart like Lego. Even the fan itself just comes out, so you can actually get to the refrigeration parts on that from left, right, front, back, or from the top, because it literally just comes apart like Lego. Okay. So I mentioned about the noise. Obviously, this is something you need to consider with air-to-water heat pumps. There's obviously a big fan on there in the garden or down the side of the house. And our unit, as I mentioned, is very, very quiet. It actually comes with the quiet mark, sort of stamp of approval, which is good. So our standard 7001 heat pump, up to 46 decibels, which is quieter than children playing, as you can see, just slightly more than birds. Our units also come with what's called a sleep mode. So if your neighbours are particularly sensitive or you're sensitive about noise, you can tell the unit between this time and this time every day, can you back off on performance to optimise yourself for sound levels, so you can make the unit even quieter between certain times. And if you were to go for the 7400 with the nose on it, like one there, the diffuser, and in sleep mode, it goes right down to 34.5 decibels, which is really quiet. An oil boiler flue terminal would be way above all of those, so it's much quieter than a flue on an oil boiler. If somebody wanted the optimum for sound, we would say 7400, but if you wanted the bigger output unit, or the customer didn't think they were sensitive with noise, but they are now, but the unit's already in, we do a sound hood for the 7001, which will remove a few decibels as well, as an optional extra if needs be. Customer benefits. So the unit itself can be controlled by the app on the phone. That's what everybody wants nowadays. Is there an app for that? Yes, there is. So there's an app for our heat pump. The unit could even be used in reverse. So you don't find this very often in the UK, but if you had underfloor heating, you can actually, in the summertime, flip the heat pump into reverse and actually pull the heat out of the slab and reject it to outside, therefore giving you a cold slab to walk on. So it's not very common in the UK, but that unit can do it. I mentioned about the fact it's got a sleep mode. It is MCS certified. We do a noise reducing hood as an accessory if you want, and everything is inverter driven. So the fan, the pumps, the compressor will all speed up and slow down with demand. Oh, skipped too many. Okay, that was the full-on heat pump that does your heating and your hot water. What about then if you've got a house that isn't heat pump ready? The radiators can't be upsized, the heat losses are too big, the heat pump will be enormous. What's the answer for them? Well, we've brought out a unit called a hybrid. Now the hybrid uses the same outdoor unit as the full-on air-to-water heat pump, but this one is not designed to be the whole solution. It works with a gas boiler or LPG or oil, and the idea is you've got the best of both worlds. The two will work together. Okay, so here we have a gas boiler. It hasn't even got to be a Worcester Bosch one. Okay, so as long as you can control it by 240 or 0 volt switching via a relay, you can run that with our hybrid. So you have an existing boiler. Has to be a combi though. So oil, LPG, natural gas. You have an internal mixing unit, which is that one there, similar sort of size to like a water heater. And then the outdoor unit is the same outdoor unit as our full-on heat pump. And the idea is that in the warm weather, when your heating demand isn't that big, your flow temperatures aren't that high, and the air outside has got a lot of energy, the heat pump can take control of your house. So that will do all of your heating in the warmer months. When it starts getting colder and heat pumps start to lose their efficiency, they start to lose their output, and your older property with its older radiators needs more power really, the units can work together. So the boiler and the heat pump work together via the mixing unit. And then if it gets really, really cold, when normally a heat pump would be costing you quite a lot to run, not very efficient, not all that powerful, the system automatically decides, I'm actually better today working on the gas boiler, so it will turn the actual heat pump off and work as a gas boiler. Then obviously as it gets warmer, it goes back into hybrid mode. So in theory, it looks like that. So we have there a combi boiler, that's doing your hot water completely on its own, and the flow and return from the heating go into the mixing unit. The flow and return from the heat pump also go into the mixing unit, and then the blending valve in that unit then decides via its controller which one am I going to use today, or am I going to use both. Okay, so that is quite an interesting product really, because there's a lot of houses out there that aren't heat pump ready, but they would like one. So maybe the hybrid is the answer. So in the hybrid we do a 5, a 7, a 9, and then in the quieter version, the 7400, we do a 5 and a 7. And you might ask, well, why is there no 13 and 17 there, like you did on the full-on heat pumps? Well, surprisingly, with a hybrid, you want to get the most out of that, rather than running on the oil boiler LPG. So we don't size them 100%. We actually size them generally for around about a quarter of the demand. So if you have a 20 kilowatt load, an older property needs 20 kilowatts. A 20 kilowatt heat pump is a big heat pump, and you've got to run electricity to that as well. But with this, we'd actually say, well, fit a 5 kilowatt hybrid. And you think, well, that doesn't sound enough. The idea is that we want that hybrid to do as much as it can. We don't want it to ever go off. So you give it a really big job to aim for. So we actually would fit a hybrid 5 kilowatts in a 20 kilowatt house, as you can see by that pie chart. So we size hybrids around 25% of the total load. So as I mentioned, the 20 kilowatt house would fit a 5 kilowatt heat pump. And the reason for that is that around about 80% of the time, a 20 kilowatt house only requires about 5. As shown on that very professional slide I put together earlier. Okay, so you can see that, yes, okay, it does need 20 kilowatts, but for what days does it need 20 kilowatts really? Very few days in the year does it need full power, but for 80% of the time, it needs 5 kilowatts. So that's how we would size a heat pump, is to take on the majority. Okay, so heat pumps, and heat pump is the phrase at the minute, isn't it? Everything's gas is going to go, and heat pumps are going to be there's things to consider, okay? They have their place, and there's definitely things we need to consider. So, in the UK, we have quite a few houses that look like that. Very high heat losses, old-fashioned windows that might not be able to be changed, existing radiators, and these are the ones that want the help on their heating bills. If you get asked to fit a heat pump in that sort of house, or can I have a heat pump in that sort of house, it's always a little bit difficult, because we need to think about, well, is that property actually suitable for a heat pump? If it's in a beautiful village somewhere, do I need plan permission to fit a big fan outside? We do use heat pumps the most in the worst conditions, so what is the efficiency of it in those conditions? We need to make sure it's sized correctly for that sort of heat pump. Is it even going to be big enough? The noise, the limit in size, as I mentioned. These units do a thing called defrost. All air-to-air and air-to-water heat pumps have to do a defrost. When they're sucking the energy out of the air and there's moisture in that air, the back of the unit will freeze. It will freeze solid and it will stop working. So in order for them to carry on working, they have to do a thing called a defrost, which means they have to run in reverse temporarily, and instead of heating the radiators, I need to heat the outdoor unit to defrost itself, get rid of that big block of ice, so then I can go all over again and do it again. Now, when that unit runs in defrost, where do you think it gets the heat from? Anybody got any ideas? It gets the heat from inside the house. So quite often with heat pumps, you'll hear these words of buffer tank. Yeah, buffer tank, or system volumizers, accumulators. We tend to use the same word, 3 different phrases for the same thing in this industry, don't we? But basically you often see a 50 or 100 litre accumulator, buffer tank, and the idea being is that the heat pump heats up the buffer tank, and then you take a pump and take the heat from the buffer tank to heat the house. So when the unit wants to do a defrost, it doesn't suck all the heat from your radiators, which it would do without a buffer tank. It can take the heat from the buffer tank to defrost itself, clear its heat exchanger at the back. So this is something you need to think about, is that, okay, so I've got an outdoor unit, I've got an indoor cylinder, I've got an indoor wall-mounted box. How are we going to run the heating system? And if the customer says, no TRVs, leave it all fully open, weather compensation, good flow rates, fine, you don't need a buffer tank. If they mention TRVs, zones, programmers, actuators on underfloor heating, we've got a situation where not only could the heat pump try and cool the property in a defrost situation, but if the system is all closed down, it might not be able to do a defrost because it can't access the energy in order to do it. Okay, so we do fit heat pumps with their buffer tanks, but only on fully open, free-flowing systems. If they want control, ideally you need a buffer tank, and it helps with it to do a full-on defrost. So you've got to put these things somewhere, and electrical supply, okay, not so much on the 5, 6 and the 7, but if you start fitting a 13 or a 17, and it is actually a requirement that you do contact the DNO, the district network operator, and let them know, I'm fitting a heat pump at this house, my electrical consumption is going to be bigger than normal, can the grid cope with this? So you are meant to ask for permission first. Okay, the last one there is about the fact that if you did use that outer energy, somebody else is going to get involved with one of your customers to design the job and to commission it, and not everybody's happy with somebody sort of coming in and into their install, which I do understand. Now I did mention quickly about a thing called an immersion heater, and some people are a little bit afraid of them, but as I said, we size the unit to 99.6% of the time. So it should hardly ever come on, maybe for pasteurisation, for Legionnaires, that sort of thing. But it only ever comes on either in an emergency or if it really needs the help on that coldest day, which we feel is much better than having a heat pump that's enormous to cope with that one day. So our unit does have a heat pump. But obviously, if you were to size the unit wrong, or it was specified wrong, or the customer didn't use it correctly, the last thing you want is it to bring on this immersion heater and then never click it off. Okay, so obviously we've got to think about that. So it must be sized correctly. It's really, really important. So we have a design department at Worcester. So if you've got a customer that's interested, again, speak to your sales rep, and they will then send the designs to their design team, and we can actually help you size the unit and make sure you get the right one. Because believe it or not, heat pumps are also sized on location. So where are you in the country? Because of the weather conditions and the heat losses of the property, it all plays a part. Okay, now another thing, if you're sort of new to heat pumps, I've already mentioned that we do a 5, 7, 9, but if that was a boiler, a 12 kilowatt boiler, and you bought a 12 kilowatt boiler, it would give you 12 kilowatts night, day, summer, winter. It's a 12 kilowatt boiler, that's what it does. But with heat pumps, when we say things like it's a 5 kilowatt, well, some days it might actually be 8 kilowatts, but on other days it might be 3 kilowatts. Because how hard are you making it work? What's the weather outside? What's the flow temperature around the heating system? There's so many variables. So when manufacturers, not just us, we quote our outputs, they're to a European standard, EN 14511, and it means that you must quote your outputs at 7 degrees. Okay, so warmer than 7, it's going to be more powerful. Colder than 7, it's going to be less powerful. So you must make sure you size it correctly. Okay, I did mention this, but it is important. Are you all aware as well the building regs changed a couple of days ago? So any new heating system now, even gas, even oil, must be sized so the radiators don't run any hotter than 55 degrees. Came out on the 16th, and it's all about getting us sort of ready for heat pumps and ready for future technologies. And obviously if we're going to run a radiator at 50 degrees maximum, ideally, the unit can do 65, but that's for hot water. Any heat pump, if you start pushing it into that sort of temperatures, it's going to have an effect on your efficiency. So we try and design a heating system to sort of run really 50 degrees or cooler. And if you were to put a radiator in a home that used to run at 82 degrees, and you now want to run it at 50 degrees, it needs to be quite a bit bigger to do that job. And that actually is the correct figure there. It's a factor of 2.4. So the radiator needs to be 2.4 times bigger than it was before. People often understand about radiators need to be bigger, but what they often don't fully comprehend is the fact that not only your radiators, but also your pipe work. So with a condensing boiler, we're looking for a delta T of 20. Standard efficiency gas boilers were sort of 10 or 11. And with heat pumps, we're looking at a delta T of 7. So you can see on a 15mm pipe feeding a radiator, with a condensing boiler, you can almost run the whole house in 15mm and it will actually work. There's a lot of play, a lot of give in that system. 11 kilowatts through 15mm pipe. But with the heat pump at 7 degree delta T, you're looking at a 4 kilowatt load. And obviously these radiators are going to be very big, so you're looking at sort of 15mm drops, sort of 2 radiators maximum really. Obviously it's up to 4 kilowatts, but that does as a rule of thumb. So the delta T does affect the output of the pipe work, and obviously the property itself plays a big part. So if we were to actually look at an existing property, and then a new build in the sort of last sort of 15-20 years, and then a south build built a very high spec, those actually are pretty good rule of thumb watts per square metre. So if we were to look at a house that was 200 square metres, so the same size house but just built to a different construction, that's how much of a difference it can make to the heat loss of the property. So 26 kilowatts, same size house but built to a higher spec, down to 8 kilowatts. So you can obviously see that the 2 newer ones are heat pump suitable, particularly the one on the right, whereas the one on the left would require a lot of work before we consider a heat pump. Okay, so what we have to offer is 2 options. Is the property well insulated, modern, new build, can be brought up to a good standard? Then in which case we have a full-on heat pump, does your heating, does your hot water. If the property can't be brought up to spec for various reasons, all is not lost. We have a hybrid solution. We also have obviously controls, buffer tanks, cylinders. So there will be a pre-plumb cylinder coming out soon. That's also going to be interesting, because you might not need the indoor unit then. The pre-plumb cylinder will have those bits fitted to it. So we have various options available. Okay, so obviously that was just a bit of a taster, just a bit of an introduction. But if you would like to know more, we do have training centres all over the UK. We also do webinars as well online, 1 to 2 hours. They're completely free on Skype. You can just sign up and sit back and listen, and we'll take you more in depth into the heat pumps that we have. But obviously, while you're here, then please speak to the people that are around in the lovely green shirts, and they'll be able to help you. If you want to go obviously properly into this, we do full-on heat pump courses at the centre. And there you actually get hands-on. You can take the unit apart, play with the programmer, get it actually work, and they actually all do work in the centre at Worcester, not only down the road from here. Has anybody got any questions? No, you've done well to stay awake. Yeah, so the hybrid is with a combi. The combi boiler, yeah, because the combi boiler does the hot water itself, high temperatures whenever you want it, and the hybrid just helps out the heating system. But the normal one does your heating and your hot water. So you would then have a cylinder with that. Hasn't got to be a Worcester cylinder, but it has to be a heat pump cylinder to have the big enough size coil inside to work at lower temperatures. Yeah.
What about the hybrid system? What's the boiler that you can pair it up or what size of it?
Okay, so with the hybrid, it will work with a boiler up to 32 kilowatts. And the reason for that is inside the indoor unit there's a blending valve, and a diameter at a blending valve will only pass about 32 kilowatts, so that's really the limiting factor behind it. Okay. Any other questions? If you get somebody to scan your car and tell them interested in heat pumps, they'll send you everything about heat pumps to the email address that's registered on the car. Okay? Okay guys, thank you very much.
So I'm fairly confident that if you come here today, you understand why we're having to transition to low carbon heating, and probably you know that heat pumps are going to be a good part of that. And certainly a big push really from government at the minute to get heat pumps moving. We've got heat pumps really that are out the front there, which you might have seen as you come in. And I want to try and focus today on these type of heat pumps, because when you're dealing with commercial, there's lots of different types of heat pump you might come across. You know, you could come across air source, ground source, water source even sometimes. You know, you've got reversible, you've got splits, you've got monoblocks, you've got all sorts of things. But without doubt, these are probably the bulk of the market really into the commercial world. These are air source heat pumps, what we call monoblock heat pumps. So all of your refrigerant, etc., is contained within the unit itself, which makes life a little bit easier. And you can cascade these. These come in 22 kilowatt and 38 kilowatt sizes. We also do a reversible one of these actually, but I'm going to focus more on the heating applications today. And so you can cascade these up into bigger outputs if you come across situations where you want to meet a larger load really. So a couple of weeks ago when I was asked to do this presentation, I was thinking about what to cover in this presentation really, and some quirky lucky thing really was that CIBSE released a new guidance document covering this very topic. So CIBSE is the Chartered Institute of Building Services Engineers, and they've just released this document here called AM17, and it's covering this very topic, and it's actually been funded by government. And because it's been funded by government, because they're sponsoring it, you can actually download this document for free. If you go onto CIBSE's website, just create yourself a registration in there and use that code AM17 and you can download it. And these documents normally cost about £60–70, so it's a nice, it's a good thing. But I think it kind of it's reflective really of the fact that there's real knowledge gaps in this area at the minute, and that's really why government have funded this document, because there's a lot of learning needs to go on, and there's a lot of questions about it. Now, the document itself covers new build and retrofit, and I could have probably made my life a little bit easier if I'd tackled the new build section, because heat pumps are a lot easier to apply to new builds, where you can tailor the system and the buildings and much better performance. But I thought, no, okay, let's tackle the harder question. I think it's the one that people want to know about. How do you try and fit heat pumps into existing retrofit systems? So we're going to have a look and see what AM17 tells us about these types of applications. So the first one we've got to think about really is sizing our heat pumps, which I guess is a fairly obvious thing. But what the document talks about first of all is approaching this in the way of actually trying to reduce your demand down a bit if you can, because without doubt if you can reduce your demand you'll get a lot better performance out of your heat pump itself. And there's a standard here, PAS 2038, which is it's a BSI standard. It's a publicly available specification, but it actually tells you how to go about doing this type of demand reduction. Now, once we've thought about that, we've really got to consider our heat losses very carefully, because we don't want to be just going into a building thinking, okay, I've got a 200 kilowatt boiler in here, I'm going to swap this out with a 200 kilowatt heat pump, because you're not going to get a very good system going that way. You really need to think about your heat losses, have an assessment of what the demands actually are, and it can be useful to try and create one of these demand profiles, and I guess it's something maybe you wouldn't have the tools to do yourself, but it's the sort of thing that we can help you with. So if you get a year's data for the gas supply, etc., we can build you a demand profile around this from typical types of buildings that you're dealing with. And it can be very useful when you're trying to see a realistic pattern of what actually might be the peak demands, and how you then size your heat pump to that. Now, the next thing that we've got to think about is what type of system are we going on to, because without doubt heat pumps need to be operating at lower systems, and my colleague Rob, who was just going through the domestic side of this earlier on, was explaining how we need to look at the the radiator systems if we're going on to that, or maybe we've got fan convectors underfloor, whatever. But we need to be pulling the temperatures down on it because we will get much better performance out of that. And I think, you know, a good part of the planning of a system like this is really around looking at that existing system and what you can do with it. Now, when you're dealing with the commercial world, traditional radiator systems can be sometimes reduced a little bit down. Maybe you need slightly larger radiators in certain cases, but a lot of radiators are oversized anyway, so it's worth having a look at that. But you can also think about things like fan convectors. You know, they operate at lower temperatures, and they can be, you know, a useful kind of tool to employ here. But there's no question. I mean, this can be a sticking point. You know, this sometimes can be the make or break of the job, whether you can actually go ahead with it. And I think, you know, I put this last kind of point on here, that not all buildings are going to be suitable for this, and we have to kind of, you know, accept that right from the start. So along with reducing our temperatures for the heating system as well, the way that we control the system is really important. Now we really need to think about using things like weather compensation, because weather compensation should really be thought of as a given when you're dealing with heat pump systems, because throughout the year we can create a curve so that we reduce the temperature down on days when we don't need that full power from the heat pump. And operating at those lower temperatures can really give us an efficiency boost. And typically, if you can drop the temperature down in your flow by 1 degree, you gain about 2.5% in your efficiency. So every temperature you know, reduction that you make, you're gaining efficiency. And the other thing that can be a useful tool here is night setback, because heat pumps like to work in a nice kind of gradual way. And so if you're trying to bring the temperature back up in the morning right up to you know, what you expected to have during the daytime, then that puts a big load on the heat pump. And night setback can be a useful tool where you just keep that temperature just topped up a little bit, and you've not got such a big gap to make up at in the morning period, and it takes the strain off your heat pump a little bit. It's often thought with heat pumps, I think they need to be controlled in a kind of gentle way, and I think the analogy with adjustment of your refrigerator is often a good one, because, you know, we're used to, with gas heating, bringing things on very quickly. We heat up very quickly. Our radiators heat up very quickly. But with heat pumps, you kind of need to make gentle changes and allow that to come into effect. And so if you were adjusting the temperature in your refrigerator, you probably wouldn't expect it to be happening immediately. And it's a little bit like that with heat pumps, really. Now, thermal stores can also be a useful thing to think about when you're dealing with control, because thermal stores, although they eliminate short cycling, which is their main use, as we develop further with the grid and the grid gets more intelligent, there will be opportunities to take energy when the grid can actually supply that easily, and to switch off our heat pumps when there's periods when there's high demand. And appliances like the CS5000 that I talked about earlier on, they've already got that kind of functionality built in. So we're just really waiting for the grid to catch up there. But it's well worth thinking about kind of future-proofing here. Now, this may seem obvious, but we've got to provide a good electricity supply for our heat pumps. And a lot of buildings were sized perhaps originally just on the site loads, not considering that you're going to potentially shift all of this heat energy across to the electricity grid at some point. And so this is a really crucial stage, particularly at the beginning when you're planning a system like this, is to really look into what the supply is that you've got onto the property available. And there is a process and a form that really needs to be gone through here. So on the Energy Networks Association, they've got a standard form which you can fill in so that you can have a dialogue with what's known as the DNOs. This is the district network operator. That's the likes of your Western Powers and your UK Power Networks and that type of thing. They typically have like a 10-day turnaround to get that back to you. But it's, you know, it's a crucial part in the process, because this again could be a showstopper if you happen to be in an area where you need to have some significant reinforcement to actually get the supply that you need. And obviously you don't want to be finding that out later on when you fitted the heat pump. So really important to do this. Typically, I think, you know, if you're below 100 amps, then it's usually a fairly straightforward thing. You're just you know, doing a notification process. But once you get to bigger systems and you start cascading them together, then it's something you really need to consider early doors. Now we're going to find somewhere to put these heat pumps, and I'm talking about air source heat pumps here, so they need to go outside. And we need clearances, obviously, for servicing, as you would do around any appliance. But you also need to think about airflow, and if you don't have enough clearance, not only from additional appliances, but from buildings and plants and the like, you can get a kind of localized microclimate, if you like, build up, where you're taking energy out of the air and you're actually cooling the air temperature down. So it's very important to maintain these good clearances around the air source heat pump itself. Of course, if you're putting it onto areas like roofs, etc., then you need to make sure the loading is sufficient, because when you come to heat pumps of this size, they're heavy weights. You know, they're big pieces of kit. If you go and have a look at the one that we've got out the front there, you'll see what I'm talking about. And another thing we have to think about really is noise. Heat pumps have got a big fan on them, and fans generate noise. And so we need to consider where we're going to put these and whether there's going to be any receptors, as they're generally known, that are going to be sensitive to the noise. So, you know, in commercial applications that could be, you know, maybe not so difficult because perhaps you're butting up to other commercial buildings, but when you're going on to residential as well, then that can be a really significant consideration. And you might need to put mitigation measures and things like that. Another thing to consider, I guess, is that generally a lot of heat pumps won't be happy near the sea. You know, if you look at most manufacturers' instructions, they'll be asking for a kilometre away from the sea, so that you don't get excessive corrosion, things like that going on. Now, believe it or not, heat pumps create condense. We're used to condensing boilers, really, where we're producing condense, and heat pumps are obviously not using gas, but they create condensate because under certain temperature conditions, we can start to get frost to form on the evaporators, and that typically happens when you're below 5 to 7 degrees, and got an example here of London where this happens for like 160 days a year. And what happens is once they get to a stage where you've got quite a build-up of frost on the evaporator, they need to go into a defrost cycle. And this lasts about 10 minutes. The part of the heat pump goes into a slight reverse so that we use some of the heat from the refrigeration cycle just to melt that condensate off, and of course that needs to go somewhere. You know, you need a drain of some sort, or what's often employed really is a kind of little soak away here. These are fairly common things, and they can be useful. You know, when you're building a plinth or something like that, you can employ one of these so that you've got somewhere convenient just to take your condensate to. Now we need to think carefully as well about how we integrate heat pumps into the hydraulic system. And I think one of the key things with any type of heat pump really is around making sure that you've got the correct flow rates, because with older systems we're perhaps used to working with 11 degrees between the flow and return temperature, the delta T. With condensing boilers we've almost got used to bumping that up a bit to go to 20 degrees. You know, that's really nice and efficient. But when we're working with heat pumps, that delta T becomes much smaller, typically around 5 to 8 degrees. And that means really that we've got higher flow rates. And it's really critical. And you see so many projects where flow rates are not being considered, maybe pipe sizes are a bit too small, and that leads to inefficiency really. So I would say, you know, as a general rule of thumb, if you've got, or do not be kind of tempted to reduce down from the connection sizes that you've got on the unit itself. You know, if you've got 1.5-inch pipe on there, then use 1.5-inch pipe to come into your system, because yeah, that's an area. If you don't get those flow rates right, you will have problems. Buffer vessels I spoke of earlier on, but they are an important part of the system. As I mentioned, we want heat pumps to be heating up you know, in a kind of gentle fashion and coming off again. And the buffer vessel gives you extra volume in the system, and it stops that cycling that can go on. You know, so we're reducing that cycling down to make sure that we really don't get more than 3 starts an hour. That's what we want to try and keep it under. So we don't want on and off operation, we just want you know, nice gentle heat up and slow down. Buffer vessel also gives us an opportunity to introduce some direct electric heating into the circuit, and this is used particularly with commercial systems where if you needed to start up a heat pump from cold, you know, in the really cold weather, you need to put a little bit of energy in the system to get things going, because heat pumps will typically have a minimum return temperature, and once you drop down below that, it can be, you know, a challenge to get the things going again. So this is really just a backup for that type of circumstance, so that you make sure that you're covered. I had a kind of very odd-looking device in the middle here, which is the way that we like to see our commercial heat pumps connected up. And this is really a system that just ensures that we got flows going in the right way. And on the next slide kind of describes that a little bit better going forward. But although it looks a little bit complicated, it's a bit like a low-loss header with some non-return valves in, really. So it's a fairly straightforward thing. But what is important when you're arranging your hydraulics like this is to make sure that your domestic hot water cylinder is not going through your buffer vessel, so it's directly connected in some way to the heat pump, so that you've not got to put all of that energy into the buffer vessel to reheat your cylinder up. That makes no sense at all. And so typically they're arranged in a fashion like this with a separate pump on, but it's very important that you select a cylinder that is suitable for a heat pump, because not all cylinders are, and you'll find many manufacturers do a specific heat pump cylinder, and essentially what that gives you is a much larger surface area on your coil within the cylinder, so that you make sure you get the efficient heat transfer that goes through. So it's really crucial. As a kind of rough rule of thumb, we're looking for about 0.2 of a square meter for every kilowatt that we put into that cylinder. But you know, cylinder manufacturers will be able to help you with that. So I spoke about flows going in the right direction before, and this perhaps gives some idea about how we connect up using this arrangement that I've shown here. And what those non-return valves allow us really is just to make sure that the flows can go in the right direction under any circumstance. So when we've got the heat pump in operation and we've got the heating circuit in operation, it's going through into the buffer vessel and out to the system. But we will get times during the operation where the heat pump's up to temperature, it switches off, and the heat system continues to run. We must make sure that the flows come back correctly through to the buffer vessel, and really that's what this arrangement is all about. Equally, the other kind of scenario here is where you've got the heat pump running, but the circuit's got up to temperature, but you want to build up the energy in the buffer vessel so that you reduce this cycling. And so this hydraulic arrangement allows all that. And it's just a kind of overall, it's a simpler method of trying to connect your heat pump, your buffer, and your circuits and other things into the system. So it's a kind of you know, it's a standard hydraulic almost that you can adopt for these situations. So just to recap there, really, I think these, I guess, are the key points that AM17 tells us about when we come to do this type of thing for a commercial application. We need to think about demand reduction. It's an important step. We need to correctly size our heat pumps, particularly if you're looking at cascading heat pumps as well. And that's really, you know, it's worth that extra effort of really going into. We need to think about system operating temperatures, and as I said before, this can really be where the most important effort you put in terms of what you're going to get out of the system will be, and that can be a stumbling block at times. We need to think about control strategies, using weather compensation, using things like night setback, etc. Electrical capacity, get in there early, get your applications into your DNO, make sure you've got that capacity available and you're not going to get caught out at a later date. Noise and spacing, I think if you're involved with the MCS accreditation for heat pumps at all, you'll find that their commissioning process is very much focused around making sure that your noise issue is not going to be a problem for neighbouring properties, etc. Don't forget your condensate. You know, a lot of people suddenly realise, particularly if they've not installed a heat pump before, a bit too late in the day really, that they need to provide some condensate because they're not naturally thinking about that. And really, yeah, focus on that hydraulic integration. Make sure you've got your flow rates and your pipe sizes are correct, because if you don't get that right, you will have problems and you will have issues with efficiency. Now, just a couple of other things I want to just touch on. Hybrid systems can be a really interesting solution here, particularly where you've got issues with the heating system itself, where you perhaps would like to come up to slightly higher temperatures, and maybe that would just bridge the gap between having to do some really significant works in the building on the existing heating system, and whether you can kind of bridge that gap by bringing a hybrid system of this sort. And they're not difficult to do. You know, when we talk about hybrid systems in commercial, we're dealing with standard gas boilers. We're not dealing with anything exotic in any way, and we're dealing with standard monoblock heat pumps here, air source heat pumps. And the vast majority of controllers, I mean, our CS5000 here will actually have all of the technology built into it ready to do a hybrid like this. So it's not like you've got to go out and get something special to make a system like this come together. But they really do have some benefits, because there's significant capital cost savings here. You know, heat pumps are a lot more expensive than a normal gas boiler, and this can really shave off some costs. It's also very useful where you need to provide some backup. We've not talked about redundancy in any way, and you know, in many ways it makes no sense to have expensive heat pumps sat there just to cover a redundancy load. You know, it's far more sense to have a boiler that would kick in under those circumstances. And as a general rule of thumb, what we find really is that if we size our heat pumps maybe around 40 to 50% of the peak demand load, we can actually cover something like about 80% of the kilowatt hours for that particular building. So that maintains your CO2 savings. You know, so you're getting good CO2 savings, you're reducing your capital costs, you've got your backup in there, and it really does make a lot of sense. And this is not only in just standard buildings really. I think you also see this being a really good applications for where you're doing smaller heat networks, etc. And I just wanted to pick up on another CIBSE document actually, which was released a short while ago, just before AM17, and it covers a similar topic, but it's actually dealing with small heat networks and communal systems. And in there, you know, this makes specific reference really to your hybrid system. So it's really worth looking at, particularly where you're doing heat networks, where you're doing using heat interface units like the one we got on here. You can have a very good, nice system together, you know, completely, almost like a package really from us. So we can do the boilers, the heat pumps, and the HIUs on the system, and you know, meet all your needs there. So it's well worth having a look at these two documents, I think. Well worth downloading AM17, because there's a lot of good information in there, particularly when you can get a hold of it for free. And I think, you know, whatever way we go with heating in the future, there's going to be a lot of learning here. You know, whether we go with heat pumps or heat networks or with hydrogen ultimately, there's learning going to go on. We're in a big period of transition. So hopefully it's kind of given you a few pointers. In 30 minutes I can't tell you everything you need to know about installing heat pumps, but I think, you know, what I hope here is this will give you a few prompts to take away and go and have a look up, and maybe get in touch with us if you want to find out a little bit more. So thanks for your attention. I don't know if there's any questions that anybody's got, but I'm happy to take a few questions if anybody's got them at all. Digest that lot, yeah, okay. Yeah, there's a lot to take in there, I know. There's a lot to it. But I think, you know, we're in a process now of just changing our mindsets about these sorts of things, you know. Some of these projects seem a lot more involved, and inevitably there will be, you know, more involvement from the installer. But I think it's just something we've got to get to grips with, really. I think whichever way we go, like I said, whatever form of decarbonisation, there's going to be learning going on here. Even if you transition into hydrogen at some point, there will be, a learning curve that we've got to go through. And I think, the quicker we all get on board with this, the easier and more comfortable we'll feel about it, really. At the end of the day, it's just knowledge, isn't it? We just got to get our heads around it, adapt what we're doing slightly differently, and, I think we'll be in a good way.
In terms of commercial, do you think we're already at kind of a point where we're doing these, or is it just a new build? So in terms of retrofitting a new build, do we feel that this is kind of more like the new build end rather than the retrofit end?
I think, like I said from the start, heat pumps are very well suited to new build because it's such an easier proposition. You can start your heating system, in the right way as you want it, low temperature, underfloor heating and the like is absolutely perfect. You've got a better performing building, from the beginning. A new build is going to be much better. And so it brings down the size of your heat pump, the cost, etc. associated with that. So I think, it's a no-brainer really that heat pumps are going to be better suited to that end. But I think the real challenge is, how do we start to introduce this into some of the existing buildings? But I think it's about, being sensible with it, looking for the kind of properties where you could do an install like this, where you can get over some of these problems that you're going to encounter, relatively easy, cutting your teeth on it and seeing how things go. To be honest, there is still a lot of learning going on here. We've got the International Energy Authority at the minute is doing what they call an annex. It's a piece of work really where they're looking into what guidance can we give you here around retrofitting heat pumps into existing buildings. And there's some interesting trials out there from government already, more historical information that has come from like the RHI program into commercial where they kind of monitor a few systems, etc. So there is a lot of learning going on, definitely.
Was to do any hands-on training?
We do, yeah, we do. We do heat pump training. Yeah, in-house. Yeah. I mean, pretty busy, but the best thing is just get in touch with us. Let us scan your badge, as it were, and if you want to get in touch with us about that, we'll get you on a course at some point. Thanks.
Is it a qualification or?
No, it's a guidance document really. So I don't know if you've seen any of the other CIBSE guidance documents, but they're well known for their guidance documents in this area. But I think what's different about this is normally we're paying quite a bit of money for these guidance documents. They are quite expensive, but this one being sponsored, it's just free to download, and there's just some really good knowledge in there. So yeah, definitely take advantage of it while you can, I'd say. Yeah, definitely.
Hydrogen heating then?
Hydrogen. Yeah, I think actually, if you go around the front there, you'll see our hydrogen-ready appliance out there. Hydrogen is both really. Yeah, we're getting geared up for both situations because we will need everything to if we're going to do a transition like this, you need to be able to pick up commercial buildings as well. But I think we're in this process at the minute. Hydrogen looks very promising where it's going. There's a lot of work been going on with it around the Hy4Heat program that's been running. We've been very much part of that. I think from the point of view of appliance development, well, it's getting quite mature now. We're really looking to the next decisions from government around are we going to go ahead with this or not, and how quickly can they ramp up the supply of hydrogen? I think that's really one of the big questions, and we've started to see recently a bit of a divergence from government thinking about in terms of, okay, we're going to tackle this from get hydrogen produced or being produced end, as well as from the actual technical side of it and the safety case and the like, really. So there's a slight divergence there. But yeah, looking very promising. But I think at the end of the day, we're going to need everything. We're going to need heat pumps. We're going to need hydrogen. We're going to need heat networks. And I think we see in the future a much more diversified marketplace. Gas is so dominant at the minute and has been for 40, 50 years in this country. But I think going forward we will see a split of you know, mild diversified appliances. Yeah, absolutely. I think, you know, what you're seeing now is the boilers that I put up on the screen there. They're natural gas at the minute, but they're already being properly certified for blends up to 20% of hydrogen. It's another step to go to the 100% hydrogen, but that's really what we've developed. But it's a case of getting a kind of clear government decision with that about how we're going to move forward and how that's actually going to, you know, kind of move on. I think we see something a little bit like they did with condensing boilers back in 2005, where they mandated, you know, condensing boilers only after that point. We could see a situation where they mandate only 100% hydrogen appliances, and you start to get a pre-population of appliances out there, and then you do a kind of conversion at some point, you know, when the hydrogen supply comes along. Well, what government have committed to is making a decision in 2026. So they'll make a decision at that point. Now, it could be that they're in a good place at that point and things happen fairly quickly, you know, but there will inevitably be, you know, a little bit of a gap there where we start to get ready for it. But I think, you know, there's a strong possibility you'll start to see some rollout from around that time, as long as we get a positive decision from government with it, really. But, good. Thanks for your questions.